Hello friends, here in this video we are going to see a problem on deflection of a stepped bar, and for that here we have a question. A stepped bar is pulled by 20 kilonewton force as shown in figure. The diagram is given to us. Here as we can see, we have this stepped bar having different diameters. At first the diameter is 15 mm, then 50 mm, and at last it is 25 mm. The length of diameter 15 mm, it is up to 1500 mm. For 50 mm diameter the length is 2500 mm. For 25 mm diameter the length is 1900 mm. So this is a case of a stepped bar having different diameters and different lengths. Next, it is subjected to tensile load. As we can see, this is a pull type of load. It is trying to pull the stepped bar, and the question is to find the total elongation of the bar. Take capital E, that is Young's modulus, 2 into 10 raised to 5 Newton per mm square. So for the stepped bar given, we have to know how much is the total deflection. So first let us write the data for this question. Now here we have to find the total elongation. I'll denote it as delta L for the stepped bar. Capital E, Young's modulus, 2 into 10 raised to 5 Newton per mm square. Next, here we have three different sections, so I'll call the diameter 15, this will be my section 1, this diameter 50 would be section 2, and here diameter 25 becomes section 3. So the diameter of the first section is 15, so D1 is equal to 15 mm. Next, D2 is 50 mm, and D3, that is 25 mm, and the corresponding length L1 is 1500 mm, L2 is 2500 mm, and L3, that is equal to 1900 mm, and the load value is given as 20 kilonewton. So I'll write it as 20 into 10 raised to 3 Newton. So this much is the data given to us. Now let us try to get the solution for this problem. As diameters are given for the stepped bar, there are three different diameters. So using them, we can first calculate area of each of the section. Solution, I'll say that since cross-sectional area of each section is given by first section 1, area 1 will be equal to pi by 4 into d square, and here we are having the diameter is 15 mm for the first section. So area 1, this comes out to be 176.71 mm square. Then area 2, it is pi by 4 into d square again. Here the diameter is 50 mm. So area 2 comes out to be, it is 1963.50 mm square. Then area 3, it is pi by 4 into d square again. Here the diameter is 25 to 25 square. So area 3, this comes out to be 490.87 mm square. Now after getting individual areas, we are going to find the individual deflections. So here I'll say that since deflection in section 1 is having diameter of 15 mm and it is 1500 mm long. So here I'll draw the diagram for that. This is 1500 mm long and the diameter, that is D1 is equal to 15 mm. So this is the first section, and deflection in this section is given by the formula delta L1 is equal to PL upon AE. This is the formula to find deflection. Since we are calculating for the first section, so this would be section 1. Now here I will be putting the values. So therefore deflection in section 1 is equal to P. The load applied is common to all of the section. Here the load applied is given as 20 kilonewton in this problem. So here we have 20 kilonewton load. So therefore instead of P I'll write it as 20 into 10 raised to 3 Newton. Length is 1500 mm divided by area of the first section, that was 176.71, and Young's modulus is 2 into 10 raised to 5. So from this I will get the deflection in the first section and my answer is 0.85 mm. After getting deflection in the first section, I'll calculate deflection in the second section. So deflection in section second, and here the diameter is 50, length is 2500, length is given and even the diameter value is known to us. It is 50 mm and this is subjected to a tensile load again having the same value of 20 kilonewton. This is the second section. So again I'll use the formula of deflection in the second section as PL upon AE for the second section. Here I'll be putting the values. So therefore deflection in the second section, load is 20 into 10 raised to 3, P into L is 2500 divided by area 2, which is 1963.50, into Young's modulus, which is 2 into 10 raised to 5 Newton per mm square. So from this I'll get deflection in second section. My answer is 0.127 mm. So now after getting the deflection in the second section, I'll say that similarly deflection in section 3 is given by, now if I look into the diagram, section 3, it was having a diameter of, in the problem it is given, it has 25 mm diameter and 1900 mm length. The load is again 20 kilonewton tensile. So I'll draw the section here. Diameter of this section is 25 mm. Length is 1900 mm. This is the third section. So deflection is given by PL upon AE for the third section. So here I'll put the values. Deflection in third section. P, it is the tensile load which is applied here, having value 20 kilonewton. So 20 into 10 raised to 3 multiplied by length is 1900 divided by area for the third section, that was 490.87, and Young's modulus, it is 2 into 10 raised to 5 given Newton per mm square. So the deflection in the third portion, my answer is, it comes out to be 0.387 mm. Once I have calculated the deflection of all three sections individually, next I'll add up all of them to get the total deflection. So here at last I can say that, therefore total deflection of stepped bar is given by, total deflection will be denoted by delta L, and that is equal to delta L1 plus delta L2 plus delta L3. I'll go on putting the values. Delta L1 was 0.85, delta L2 0.127, and delta L3, this value is 0.387. Now after adding them, I'll get my answer as, it comes out to be 1.364 mm. Since this answer is positive, it means there is elongation of this stepped bar. This is the answer. And suppose if the answer would have been negative, it means there is decrease in length, and that is called as reduction. So here, as we see in this problem, they were telling us to calculate the total elongation of the stepped bar, and we have found out that value, that is 1.364 mm elongation, and with this we complete the question.